Here. Okay, thank you so much for joining us. Welcome, everyone. Mirko is going to be talking about new partition identities from C1L modules. Feel free to start whenever you're ready.
Well, thank you. Hi, everybody. I thank Floor and the seminar, representation theory seminar, for inviting me. So I'll speak about this joint work with Stefano, Arnie, and Andrei. Andrei, he's not a mathematician, but he helped us write the code so that we could test numerically our ideas. And we came with two conjectures. One is related to standard modules of symplectic affine Lie algebras. And today I'll formulate this conjecture and then try to explain some representation theory background of that conjecture. So, so what I should do now? Okay, this is commercials. Okay, so classical Rogers-Ramanujan type combinatorial identities. I'll write a partition in terms of frequencies of the parts that appear. Rogers-Ramanujan identities are two identities for A equals 0 or 1. And they say that the number of partitions of n such that this difference condition holds, fj plus 1 is less or equal to 1, and that this initial condition holds, f1 is less or equal to a, equals the number of partitions of n into parts satisfying this congruence condition. So this difference condition is saying that two parts, j and j plus 1, like 1 and 2, cannot appear simultaneously. So if one appears, the other cannot in the partition. Gordon has generalized Rogers-Ramanujan partitions for any k greater or equal to 1 and a in between 0 and k. And here, so it is partition satisfying difference conditions and initial conditions that equal the number of partitions satisfying that part satisfies some congruence condition. But this difference condition is a bit different. So fj plus 1 is less or equal to k, meaning that two numbers j and j plus 1 can appear at most k times in one partition. And of course, this is the initial condition. So now I'll skip a lot of history and I'll say a theorem that was proved long time ago. It is about colored partitions. We write n as a sum in terms of frequencies and parts A. So here A are parts in the array of natural numbers denoted by n3, which consists of 3 rows. One row, the first row is odd numbers. We will color them red. And the other 2 rows are all natural numbers. We will color them black. And so in our partition, if we have a part red 3 and 3 and black 3, we will count them like in cards, just as 3. Also, this array is arranged so that the position matters. So starting from some element on the top, we can go down, and like starting with 5, we can go down 2 ways, to 4 or to 6. So here we choose 4, and from 4 we can go down to 3 or 5. So here is one downward path, so we should call it. And altogether there are 4 of them, it's clear. So now our theorem states that having two non-negative integers, the sum k being positive, then the generating function for the number of colored partitions n with parts in this array, satisfying such that they satisfy difference condition. So for any downward path, the sum of frequencies should be less or equal to k, and that satisfy initial conditions. Here it means that frequency of black one is less or equal to k naught, and the frequency of red one is less or equal to k1, is the principally specialized character of standard module for a affine Lie algebra of type A11. So due to Lepowski's product formula, these are Rogers-Ramanujan type combinatorial identities. And here it should be just noticed that this difference condition is more complicated than in Rogers-Ramanujan case or in Gordon case for in general K. So today's conjecture is really that similar identities hold for all standard modules of all symplectic affine Lie algebras. So let n2l plus 1 for L greater or equal to 1. So for L equals 1, it would be n3 that we just saw. But n2l plus 1 be the array of one copy of odd numbers and L copies of natural numbers arranged in two L plus 1 rows, so that going up or down to the right on any diagonal, numbers increase by 1. So this should be something like that. For n equals 5, we have 5 rows, and we start with ones on the left, and going down or up on any diagonal, we increase numbers by 1. So we can, starting with these ones, we can fill the whole array. So number 3, for instance, appears 3 times here. So we should think of it as that one is colored in color, say red, another in green, and the third one in blue. So we shall consider colored partitions of n with parts in this array. So A are in this array, and this is written in terms of frequencies. So the partition is determined by its frequencies, its array of frequencies, because for each point we should have a frequency. Of course, all but finally many of these frequencies are 0. For example, in the colored partition 6 equals 3 plus 3, red, both red, we have the frequency of red 3 is 2, and all other frequencies are 0. So the colored partition is determined by the array of frequencies f, and I'll write something like that, f1, 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 and it looks the same, but it's not. So this f1 refers to 1 on the top of the array, on the first row, and this f1 refers to the one on the bottom row. So it comes obvious if we color like 3, if we color 3 in red, green, and blue, then it is clear that it is different f's. But so we will skip this coloring. And of course, again, we will have downward paths. So starting with 7, f7 at the top, we could go 2 ways, to f6 or f8. So we picked f6, and then we can go down 2 ways, to f5 or f7. So we'll have these downward paths. We chose this blue one. For a natural number k, we shall say that the array of frequencies f, this one, say, satisfies level K difference conditions if the sum of frequencies is less or equal to K for summed over Z, and this should hold for all downward paths in our array. So for points like far right to from the beginning, like F7, we can have array all the way to the left to F3, the downward path all the way to F3. So we have two L downward paths if we are far enough from to the right. Okay, so this is more complicated than Gordon difference conditions. We have actually, depending on the size of the array, quite a few of them. So now for parameters K0, K1 to KL, we should parameterize really highest integral dominant highest weights of standard modules. So K0, K1 to KL are non-negative integers, so that the sum is positive. And then we shall say that an array of frequencies black F. So black F, this is what is written here in black, is K0 to KL admissible if the extended array of frequencies F with upper K0 to KL in red satisfies level K difference conditions. So what I did is to add to this black frequencies F imaginary frequencies. So next to the rows that are reserved for even numbers, we put 0. Here 0 and here 0. And if we had bigger array, it would be again another 0. And then for odd integers, so starting from the last row, we put K0, then K1, then K2, and all the way to KL in general. So our black F satisfies difference K condition, level K condition, a level K difference condition, but with this added imaginary frequencies, we added several new conditions on the array. So we shall say that colored partition with K0 to KL admissible arrays of frequencies are admissible colored partitions with these parameters. So for example, if we put K all the way down and the rest 0, then we look at the downward path that goes from the top here straight down to K, and the sum of frequencies should be K. So this forces all the frequencies on the places which are denoted blue to be 0. So in K not admissible partition, we will have no parts 1 and 3 from the top row, no part 2 from the second row, and no part 1 from the third row. This will be initial conditions. So now we can state the conjecture for L greater or equal to 2 and K greater or equal to 1, that the generating function for the number of K0 to KL admissible partitions on the array N to L plus 1 is the principally specialized character of the standard module for symplectic affine Lie algebra of the type CL1. So we, as I said, we had a program and we could calculate things, and numerical evidence for this conjecture is, this does not look impressive, but still it was a lot of calculations for certain n, k, and l, so we can calculate admissible partitions, and we can calculate what comes up from specialized character, and it fits. Due to Lepowski's infinite product formula with the period 2L plus 2K plus 2, these are conjectured Rogers-Ramanujan type combinatorial identities for colored partitions. So it is clear that one side satisfying difference condition is on an array that is colored. These are colored partitions. But when we calculate this Lepowski's infinite product formula, say for this is level 2, the sum is 2, L is also 2. So this is 2L, this is 4, and 2K, this is 4, and plus this 2 is 10. These are partitions modulo, part satisfying congruence condition modulo 10, but then say 1 appears in 2 colors. As for maybe another example, the same level 2 and L is 2, we have different initial conditions, and then it is different partitions. So, okay, there are details that maybe should be commented, but I'll go further. So the representation theory background of the conjecture. So if we rotate in our example, N5 clockwise for pi fourth, we get a slanted picture of our N5. So what was vertical, now we see slanted. It's 1, 1, 1 at the beginning, and then 1 diagonal becomes horizontal, and we go adding numbers 1, 2, 3, 4, 5. The other diagonals become vertical, and what was downward path becomes something what we'll call a cascade, this downward path. So I added to make visible triangles in the background. So you will see one black triangle, and then next to it is another red triangle. And this is all red, except that I want the example of downward path. So, and then we would have another black triangle below this red one, and then adjacent to it, another red one, and so on. And on the top, it is just a little bit that's, we'll see what it is. So these triangles come from representation theory. This is what we will see. And this downward path, our example before, now became a cascade, like a little waterfall going horizontally, then falling down, and then going horizontally. So we'll take finite dimensional simple Lie algebra G of type CL, and we'll write a basis BL. So we'll start with G and Cartan decomposition with Cartan subalgebra H in red, and then N plus being the sum of all root subspaces for positive roots, and N minus the sum of root spaces for negative roots. And then looking at the root system, we will mimic denoting the basis. So for parameters numbers A and B in between 1 and L, we fix root vectors in G denoted as AB. For the root epsilon A plus epsilon B, then A subline A be underlined for the root minus A minus epsilon A minus epsilon B. So where we see minus, we will make underline. So A underline B is for the root epsilon A minus epsilon B, and A will denote a simple co-root HA. Now we write that 1 comes before 2 and so on, and L comes before L underline, and this comes before 1 underline. And then we can arrange this this basis of our simple Lie algebra of type CL into a triangle. So we start with the first column that has index 1, and we go down by this rule: 1, 2, 3, 3 underline, 2 underline, 1 underline, and so on. And we will write neatly in this triangle all these root vectors. In red, we see a basis of Cartan. This is a simple co-root H1. This is simple co-root H2, and this is H3. And then it will be important, the highest root is 1, 1. This is the highest root to epsilon 1 in CL. And this is the lowest root. And then we have simple roots, root vectors corresponding to simple roots. Epsilon 1 minus epsilon 2, this is the first simple root. And we have this root vector for first simple root, for the second, and for the third. Looking at it as a Kac-Moody Lie algebra, it will be Chevalier generator E1, E2, E3, and below we shall have F1, F2, F3. Okay, so this is the basis of n minus in black. We can write the formula, but it doesn't matter. So now we pass to affine Lie algebra. We want to write the basis. So G hat is G tensor Laurent polynomials with at its center. We'll write x tensor t to the n as x sub n or x of n. And then we have a basis. We take x in the basis of the finder dimensional and tensor it with t to the n. And we collect all of that and add the central element. We got the basis of G hat. So now we have a triangle decomposition of G hat into n hat minus plus h hat plus n hat plus, where n hat minus is finder dimensional n minus times t to the naught plus G tensor t to the n for all n negative. And then we have this part of the basis BL negative, which starts with this x naught for x in finite dimensional, BL minus, and then all the rest. And we shall write this as the array composed of a sequence of triangles. So this will be an array. It will look like this if we turn it around. So these are black. These are finite dimensional vectors, basis vectors of G, tensored with t to minus 1. Okay, so these are finite dimensional tensored with t to minus 2. And here is a bit finite dimensional of n minus tensored with t to the naught. And now we placed one triangle adjacent to another one with legs. And then we'll follow further with black triangle down and so forth. So the rule is that we look hypotenuse of the black triangle, which is the adjoint representation for our finite dimensional G. So this is the root vector for the highest root. And then we go all the way down to the lowest root vector. And so this will be repeated. And so also here we start on the other side with the highest root vectors are going to the right, will come to the lowest. So this is the rule how we put triangles together. But what really matters is that this is a crystal that is oriented colored graph with arrows hidden. So the point is, when I pass from one column to another, I add a negative simple root. So between triangles, it will be negative alpha naught. So between this column and this one, it will be negative alpha 1, and so on. So I didn't write this here, but it is important because in the principal specialization, we give degrees to basis elements. So we start with giving a degree to Chevalier generators. So in this case, for affine, it will be generator F0, F1, and F2. And we will give degrees, each of them will be degree 1. And then we will go down, filling at each step going to the right or going down, we will add 1 degree. So we'll end up with our array N2L plus 1. So we want to enumerate a basis, enumerate a monomial basis in our module. So we have Poincaré-Birkhoff-Witt monomials in basis elements acting on the highest weight vector. And a little problem or big problem is that universal enveloping algebra is not commutative. So when possible, we think about this monomial in symmetric Lie algebras. And these monomials in these basis elements of this basis BL minus hat. So, so now we have these elements of the basis coming with powers on NB. So now we have a rule how to see that it is a K not to KL admissible monomial if the corresponding array of powers, which will become frequencies, is K not to KL admissible. So we have another conjecture, conjecture 1, that K not to KL admissible monomials in symmetric Lie algebra n hat minus parameterize the weight basis of the standard module for symplectic Lie algebra with these parameters. So this conjecture implies conjecture 1, since for the principal specialization, our monomial gets to have a degree that is how many times we took this B from the basis. This is NB times degree of B, but this is just colored partition on our array. So it's clear counting degrees of basis elements will give us a character for principal specialization. So the first theorem that we have is it's not the proof of the conjecture. So it says something that for K not admissible monomial vectors, that they span the vacuum module. So it's not what we want, but it's in the right direction. about the proof. So we need relations on the level K standard module. And these are the coefficients of vertex operators on this VOA, universal VOA. So we keep the notation that N is generalized Verma module, and some other people prefer VK of G. So this is the universal VOA. And then we look at the singular vector, and we generate a finite dimensional representation R in this VOA, and we take all the coefficients. So this R bar is a loop module, which comes from vertex operator structure, and L of lambda, standard module, is the quotient of standard module is a quotient of Verma module and the maximal submodule of Verma module, which can be written with these relations in this way. And this is the consequence of Bell-Katz formula in a way. And then these relations are zero on this quotient. So by choosing a good order on our monomials, each relation which will be an infinite sum of these monomials, will have a leading term which we will single out, and then a linear combination of higher monomials, and this thing will be zero on our module. So by using a relation in induction, we can reduce the spanning set to the set of monomial vectors, which contain no leading term in any relation R from this set of R bar. And now this is the general prescription, and one only has to know what are all leading terms. And with Tom Oshikic, we found out that for CL1, all leading terms are monomials built in such a way that we take a cascade or downward path and take B from that cascade to the power NB, so that the total sum of powers is K plus 1. So if we eliminate from the spanning set monomials that don't contain this, it will be really colored partition on the array that satisfy difference K condition. And we can prove that this is a spanning set only for vacuum module, because it gets to be complicated, and we really didn't try to put this through. The second theorem that is related to our conjecture from the representation theory is that the set of 1, 0, 0 admissible monomial vectors is the basis of standard module L of lambda naught, but for all symplectic Lie algebras. About the proof here is really to try to find a Grebner basis or Grebner type basis for the maximal submodule R bar n of lambda of this n of lambda, which is vertex algebra. So we have here obvious spanning set relation times monomial vector. And there are too many of them, and we have to reduce this to a basis. And for this, we read relations among relations, and it gets to be difficult business in general. So Siladic was already in long way back, constructing Brebner basis for B21, which is equal to C21, by using program gap. But the problem was that the set of leading terms was a mess, and one could not make any sense out of it. There is another important theorem that is related to this conjecture. Evgeny Fagin, Fourier, Littleman proved that the set of K, they didn't put it this way, but this is what they proved, that the set of K0 to KL admissible monomials, but with B in finite dimension BL minus, which is in symmetric algebra of N minus of finite dimension, parameterize a weight basis of the simple module on the top of our standard module. So this is precisely the theorem. So this is all the good news I can tell about the conjecture. So in summary, conjecture 1 is true only in this one case. For all else, in general, even the spanning is not known. So one would think that maybe one could combine this theorem of Fagin, Fourier, Littleman that says something about the top of the module with the rest of, but it's it will be more than just observation. So this is sort of the glass is half full. It's not half full. It's almost empty. But the good news is the other one. So for C3, we have a Z grading of our symplectic G into G minus 1, G0, and G1. And these are commutative. It is like, okay. So looking at the basis of our C3, the basis of G1 is this upper triangle. And this is the basis of a commutative Lie algebra. And then this looks like SL3 or GL3, and this is another triangle. And then this upper triangle can be seen in a bigger affine Lie algebra, C6. So C6 would have the bigger triangle, and then the bigger red GL6, and then even bigger is black part. So the thing is that B3 is similar to the basis B6 prime of G1 for C6. So I'll not go into detail what really exactly it means. But then if we make the array of B3, what we are looking, and if we make the array of B prime 6 of these one commutative things, then we get a theorem, Trubčević, that the set of K0 KL admissible semi-infinite monomials parameterize the weight basis of the standard module for symplectic. So the good thing about this theorem is that it holds for all standard modules. The combinatorics is K0 to K admissible, okay, semi-infinite monomials. So what it means is that we take our array B hat, and then at any point we make infinite on one side, we fill with infinite imaginary frequencies. And on the other side, we look at the polynomial. And then we get a basis that is combinatorially almost the same as the one that is in our conjecture. So in a way, this theorem is a commutative version of our conjecture one, and one should hope that maybe it can be used to prove. About the proof of linear independence for A1, 1 equals to C1, 1. So here is an interesting thing, that our conjecture is for C2 and up, but the real beginning is A1, 1, and this has been done. And so the first theorem I was mentioning was proved by constructing a Grebner basis of the maximal submodule R bar M of lambda over Riemann module M of lambda. There are other independent proofs. So Boris, Fagin, Keden, Lochter, Miva, Muhin used coinvariance and Boa fusion rules for SL2 heads. So it's completely different thinking and proof. And then Evgeny Fagin for vacuum modules used, well, something was similar was used in this previous paper, but he uses Lie algebra deformations and principal subspaces. And our theorem before I was mentioning is really about commutative principal subspaces. So Evgeny Fagin came up with fermionic character formula. And so I for this basic module AL10, I wrote the formula. It is a formula like this. So there is besides principal specialization formula by Lepovsky that gets to be a product. There are Wakimoto's product formulas for characters, for certain specialization of characters. So Borcha was, let's call it Borcha's duality based on these Wakimoto's formulas, is actually that the equation, equality of characters, that 1,2 specialized character for A11 of level K with K not singled out equals the principally specialized character for vacuum space for A22 of level 2K plus 1 and K singled out. And this works for all K. So if we specialize our basis in this way, 1, 2, then we get the identity. So for K0, K1, the generating function for admissible partition of 1, 2 specialized array B3 minus, which is written here, is the 1, 2 specialized character of A1, 1K, not K1. So what it says that that K not K1 admissible partitions on this array is equal to this or equal to this product that comes from A22. So for K equals 1, we have, this is exactly Caparelli's identities. So when we look this difference conditions, they spell exactly what is in Stephanos' identities. So we see in for K equals 1, identities for A22 in this in this sort of construction with 1-2 specialization. So what is the thing that for k equals 1, these difference conditions coincide as well, and we don't know what happens in general. So we didn't figure it out by now. But there is an idea. Okay, so if we specialize this character, then we have analytic identities of Caparelli identities. And to me, it looks a bit different than other formulas that are written. Shashank, am I right?
Yeah, it's different from what I have with Matthew.
Yeah. But so what one would think that maybe if for A11 equals C1, these things happen, maybe it will be happening something interesting later on. And finally, by using Wakimoto's product formula, Flora, am I okay with time? I was afraid of the this is.
You're doing great. Yeah, we still have 5 minutes.
So, so by using Wakimoto's product formula for specialization 2-1-1 of basic module for symplectic C2-1, and the construction that we have with Tomo, we get the identity. So we have to specialize the array. So the number of colored partitions satisfying level 1 difference condition on this array. So here are already taken care of the initial conditions. I didn't write the frequencies or the parts that frequencies must be 0. So we have these triangles corresponding to finite dimensional a joint representation, and within a triangle we move by step 1. So it is 2, 3, 4, 5, 6, 7 going any way, and passing from one triangle to another is this 2 of alpha naught. So this what happens is that except at the beginning, here appear all integers twice. So we have 4, 4, 5, 5, 7, 7, 6, 6. All of them appear twice. And so the number of colored partitions satisfying level 1 difference condition on this array equals the number of partitions of n into parts not congruent to 0, plus minus 1, plus minus 6, plus minus 7, 8 mod 16. So now the question is this maybe an A42 combinatorial identity? Because maybe there is Borcha's correspondence that works in more general. So this would be some analog of Caparelli's identities for higher ranks. Okay, I'll finish here. Thank you.
Thank you so much, Mirko.
Yeah.
Any questions for Mirko? Please feel free to unmute yourself and go for it.
So this is supposed to be for the A42 for the whole module, or just the vacuum?
So this is a done question. This is a theorem. So this is the theorem. This is coming from symplectic C21. So we know a basis for a basic module, and then we specialize character 211 of this, so that we have Wakimoto's product. and Wakimoto's product will give these congruence conditions. And the specialization gives this. But so this is a theorem that comes from specializing the conjecture 1 prime. But the question is, like here, we had characters for A22 that were corresponding to characters A11. So the question is this happening also for A42 that will, so again, it seems that it should be that level K module for C2, 1 will correspond to level 2K plus 1 modules of A42. And and this representation maybe should be like L of 3 lambda naught for A42. But it's a speculation. So I thought this might be interesting because you have a lot of conjectured analytic and proved analytic identities, which you don't know the combinatorial interpretation. And of course, Nandi was doing level 4, and this is missed in this correspondence of Borcha. So this level, odd level representations of A22 are simpler, it must be.